My name is Ansgar Meroth. I'm the founding dean of the Faculty of Engineering at the GIU, and together with my colleague Horst Schulte, I would like to guide you a little bit through the program of the Faculty of Engineering and hope to help you finding the right choice in your major. During the next slides, we show you the differences and the main contents of the different majors. And later on in a Q&A live session, we are ready to answer your questions in person. So let me guide you a little bit through the program of the Faculty of Engineering as it's planned now. And you may ask, what of the 5 different majors could be the best for me? As you know, the 5 majors were developed in collaboration with Heilbronn University of Applied Science and HTW in Berlin, which is also a big university of applied science. And Horst Schulte will introduce himself later on. These are the partners who contributed to the development from the German side, and myself, I am from Heilbronn University.
My name is Horst Schulte. I'm from University of Applied Science, Berlin. I'm responsible for control engineering, mathematical modeling, and control theory courses. Additionally, I have also 2 courses about power systems, particular power systems which are sustainable in the future. So that means to produce electrical energy by renewables like wind, PV or solar PV, and this is also my research field.
We are addressing big questions for you. We say as engineers we help to ensure that humanity can continue to live peacefully and prosperously in the future. And our majors address important aspects of these questions. For instance, how can we supply the energy of tomorrow, and in particular electric energy, in the most sustainable way? Or how can we keep up individual but sustainable mobility with lowest carbon footprint, or plants that produce high quality in an efficient and competitive way? So when we started designing the Faculty of Engineering, we decided to have these 5 majors: Automotive Mechatronics, Robotics and Automation, Manufacturing, Electrical Power Systems Engineering, and Automation and Control Engineering. And the question is, what is your best choice? And what we can say by heart is that the best choice for you is the one that suits you most, basically the one that you like most. So you can ask yourself, do you like working with machines and materials, or rather with computers and electronics? Or do you like cars or robots or big machines or power plants? Or would you rather program a robot or build a robot? These are some questions you should ask yourself, and then we can go through our majors. Let's start with the mechatronic branch. So what is mechatronics and why mechatronics? Mechatronics is the synergetic integration of physical systems with information technology and complex decision-making in the design, manufacture and operation of industrial processes and products. So when we talk about mechatronics, we talk about mechanical engineering with actors, electrical engineering with drives and information processing, and sensors. And this integrates to a basic system, which of course needs a power supply and is embedded in the environment and is interacting with persons, with people, and takes information from outside. That's the basic idea, and you can project this idea to automotive, to machinery, and to robots. So let's go to automotive. In automotive mechatronics, we talk about the cars of the future and of the present. And the cars of the futures are all about automation and electricity. However, there are continuous challenges also in the more conventional fields. So you learn to understand the dynamic behavior of a vehicle, which holds, of course, for conventional and electric cars, to understand the stability of the car structure, to understand the collaboration of electronics and mechanics, and to measure and control physical quantities. So the program is not only aimed to automobilists, but to generalists who are working at the link between the disciplines, for instance, in creating the specification, testing, application, and also maintenance, and apply these disciplines to the field of automotive. Next, manufacturing engineering. If you want to manufacture a product, you have to know a lot about its physical properties, for instance, how materials behave under stress and vibrations. And you learn which steps of treatment you have to apply on a material in order to give it its shape, so you form the material, and its properties. And of course, you learn applying machines to manufacturing. Now we come to two subjects which look at the first sight very much alike. This is robotics and automation and automation and control. I start with robotics and automation as a discipline of mechatronics, and later on I hand over to my colleague Professor Schulte, who explains you the particular ideas of automation and control. So, robotics and automation. Robots and automated machines are mechatronical products that create actions automatically. So they use power to do a mechanical work. And of course they use information. And so in robotics and automation, you learn to design robots and machinery.
From my side, few thoughts and information to the program Automation and Control. In our program, and actually many engineering programs around the world, we define control to be the use of algorithm and feedback in engineered systems. Actually, feedback is a central feature of life, and we, as engineers, we exploit this central feature of life in our machineries. I would like to explain this feature with two sentences. So, on one hand, you have a reference value or a reference signal, and you compare it, on the other hand, with a real value, a real signal, which is typically a measurement of the state of the machine. For instance, the position, temperature, and you feed back this measured signal and compare it with the reference value. And the difference will be used from the controller. Our controller is actually an algorithm which decides how the machine must be driven to achieve the desired behavior. At its core, control is an information science. So it includes the use of information to steer the device, machinery or plant in such a way that it follows a desired path, hold a set point. So on one hand, control engineers are generalists. They have a broad knowledge about techniques to understand the behavior of engineered systems. We use mathematical models, we use simulations and methods to design and implement controllers. This is the core of the program, to know how we can design controller in a systematic way. On the other hand, we need also knowledge about the systems under control. So we have to know not too much, because typically we work with other experts about the plants, devices. So in our program, we have experts, and also in the other programs in the engineering faculty, we have colleagues which are experts in robotics, automatization of cars and power plants. And as a control engineer, you work together with these experts. And you are the experts of everything, because you have to design a controller to steer the machinery. So you have a direct link to different applications, and you use your knowledge to design a controller in such a way that this machinery follows desired pass, for instance. But at the end of the program, you are not restricted to these fields. You can use other ones. After you study, you can apply your skills to new things, which you may not know today, because you have a systematic skills to control new things. Electrical power systems engineering has three main topics. First, generation of power using power plants, conventional power plants, or distributed renewable ones. Then the transmission. After the generation, you have to transmit the power. Normally, the consumer and the loads are not close to the generation. And the distribution. Distribution in a huge city or distribution in a village area. The engineering methods of power system based on the fundamentals of electrical engineering that have some special topics. For instance, you have to learn how you have to transmit power using AC and DC lines, because it's more and more important to transmit the power over long distance. To reduce the losses, you can use so-called high voltage DC lines. Another important topic is the control of distributed power system based on fluctuating energy. This fluctuating energy caused some new problems which we don't have in the past. In the past we had some few huge power plants. These few power plants produce all the energy, and the few ones are easy to control compared with a distributed network of fluctuating energy. This is one of the challenge here. Another challenge is to also to integrate power systems in other energy distribution systems. For instance, gas, water, infrastructure. So power is more than electrical power. It's also related to other infrastructure systems. It's a very interesting program. And last but not least, this electric power system have to be controlled. So you have here also a link to control engineering, because distribution means you need more intelligent networks, more intelligent devices to distribute this kind of fluctuating energy.
Let's have an insight into the particular majors. As you can see with the colors, they have a lot in common. And this is not because we are lazy, it is because we are convinced that you will need these commonalities for your personal development and especially for your development as an engineer. Let's start with the personal development on the right side. We have a lot of general science and engineering, like management, languages, chemistry, science, and production. This is common for any engineering major, for your personal development. Then the two blue boxes show you the commonalities between the mechatronical subjects. For instance, the basic of mechatronics like math, physics, mechanics, materials, electrical engineering, and of course software and computers. But on the other hand, control, with control theory, system dynamics, computer networks, communications, and sensors. And then in automotive, we learn about automotive technology, and then the thermo and fluid dynamics, which is important for drives, but also for the heat management in a car, even in electric cars. Then powertrains, consisting of a conventional or an electric engine plus a gearbox, and electric machines in particular, and as well as power electronics, which is also important for conventional drives. In robotics and automation, we have basically the same foundation, but we talk about robots here. Kinetics and kinematics of robots, robot programming, robot applications, mobile robots, and other automation disciplines. In manufacturing, again with the same basics, we talk about machinery, for instance, manufacturing technologies, materials, machinery, and robots. And now I hand over again to Professor Schulte.
As the programs before, the electrical power system engineering program has 4 areas. So we have first the general science and engineering, which is common in all programs in our faculty. The control is more or less common, so we have some specialization, but the basic control theory, the system dynamics is the same. But here we have more network science and little communication, which is important in electrical power systems and future power systems. Then on the left hand side, the basics of electrical engineering as a part of the electrical power system program. Math and physics, it's common in all. Electrical engineering with some special courses in transmission and generation. Actually, generation with synchronous machines, with converters. Here electronics is an important part, power electronics, particular, and software, because software is a part also, it's also important electric power systems to control electric power systems and also to monitor based on software systems. And the core, the fourth area is the power area. Here you learn how you can use power electronics and electric drives, also power electronic in transmission systems. The electric facility is more related to planning and organization, to plan facilities, infrastructure systems. This is less research and development, it's more organization, it's more combination of given devices into infrastructure. Then electromobility is related to electric cars and the infrastructure. Renewable energy is the generation of electric power using renewables, wind or sun. So you have here devices, wind turbines, you have PV systems or solar thermal plants. And the transmission. This transmission, it's typically in the high voltage area, so we have to know how you can calculate and how can you design high voltage devices. Because here in high voltage you have high electric fields, and there's the behavior is a little bit different from the behavior in the low voltage sheet. Yeah, that's it from this program. Now, automation control diagram has the same structure as the program before. We have 4 areas. The first area is general science and engineering, the same courses as the other programs. And we have here on the left hand side the basics of electrical engineering, so the same as in the electrical power system engineering. We have the math, we have physics. We have electrical engineering, the fundamentals of electrical engineering, with some gains more related to signal and systems, so more related to the system view than electronics, and electronics also more related to signal processing, to the hardware of measurements, the hardware of actuators. And software is an important part, because at the end the control engineer implement the controller in a piece of software, so you're also a kind of software engineer responsible for the functionality and the security of the code. Then the automation area This is special for automation and control because here you learn about industrial PLCs, which are normally integrated in manufacturing processes or chemical process. It's a standard, a worldwide standard PLC, can you find everywhere, and it's necessary, yet you can learn and yet you can program this kind of devices. You see here an example of this kind of devices. A PLC is actually a special embedded computer which interfaces, which related to industrial components and devices. Digital signal processing is about the art how you can control, how can you manage a continuous flow of analog signals into a digital computer. So you have to transfer the analog signal into a digital one. So you have some interesting things about sampling in time and discretization of a continuous value into a digital binary pattern. Then the third thing is in automation is the control of drives and networks. So we have two things, the control of electric drives and other kind of drives, and the control of networks. It is also an important part, more and more important part in automation to control devices and machines over digital networks. Last but not least is the control area. Here classic control in the frequency domain, time domain, with the stress on modern and advanced control. Here you learn modern and advanced model-based control techniques, and this is unique compared with other programs because as a control engineer you are more related and you are more into control theory field. You have to know how you can use modern mathematical tools like linear matrix equations, infinite control design, optimal design, model predictive control. All this kind of control techniques is here embedded in this area. And at the end, communication and sensors is also a part of the control area.
We are through the first presentation, and I would like to thank you for your attention, and I hope that we will meet in our live Q&A sessions and hope that we can answer your questions and give you at least some hints for your best choice of your major. Thank you very much and see you in the live session. Bye bye.